My name is Thijmen Klijn Velderman from the Vrije Universiteit, Amsterdam. And I'm here to talk about the measurements of the hyperfine structure of HD+ through radiofrequency spectroscopy. Well, we've already had a few talks on HD+, there were some excellent introductions, so I won't take too long. We do measurements on HD+ to be able to test QED theory. Theory predicts vibrational rotational transitions in HD+ very well. Hyperfine structure not so much. So for H2, for example, H2+, the theory can predict hyperfine structure very well, but then if you try to do it for HD+, some discrepancies arrive, which can potentially be very interesting. So our predecessors at our group, they looked at HD+ previously, and they measured the transition frequency between V equals 0. Between V equals 0, L equals 3, to V equals 9, L equals 3. And they did this using 2-photon Doppler free coherent 2-photon excitation, after which they dissociated from this excited state, and the amount of dissociated HD+ would be their spectroscopy signal. So even though these two frequencies are not an exact match, the difference frequency put them deep inside the lambda regime, so that would be Doppler free. And then what they did is actually they measured this transition frequency twice, once from the bottom in this hyperfine interval to the bottom of the hyperfine interval in the excited state, and then once again from the top level in this hyperfine interval to the top level in the hyperfine interval in the excited state. And this allowed them to determine the spin average transition frequency, which they used to achieve tighter constraints on the proton-electron mass ratio. And also, if you look at the difference between these two frequencies, it gives you the difference between the two hyperfine intervals. So that's what they found. And the transition frequencies between the two hyperfine components, they were able to measure with an uncertainty of 0.6 to 0.7 kilohertz. And actually found a discrepancy of 8.2 kilohertz, which is 4.1 sigma, discrepancy between their measured value and the theoretical prediction. So this is very interesting. And what we measure directly builds on this finding. So our job is now to try and place this discrepancy, find out where it comes from. Is it hiding somewhere in the bottom hyperfine interval? Is it in the top hyperfine interval? Is it in both? So that's what we're trying to find out. So this is the experiment that they used and that we still use. So here you see the two spectroscopy lasers counter-propagating. We have a 330 nanometer, which you use for Doppler cooling of beryllium. We have a beryllium ion in our trap here, which we use to sympathetically cool HD+. Here it's also their dissociation laser. Magnetic loop antenna, which we use for RF spectroscopy to induce spin flips. And then we have an EM-CCD camera, which we use to collect the fluorescence from the beryllium, which in the end serves as our signal. We have our ultra-high vacuum chamber in which our trap is placed. We have a vacuum of 10 to the minus 10 millibars. In our trap, we can trap around 1,000 to 1,500 beryllium ions and 50 to 100 HD+ ions. So this is a picture of our vacuum chamber. So here is the entrance of the lasers, these two. And on the other side here, these lasers enter. This is a typical beryllium crystal, which we load. And then when we load HD+, you can see that the HD+ doesn't actually fluoresce, but it leaves a dark pore in the center of the crystal. So this absence of fluorescence is how we see the HD+. So what we want to measure is this frequency difference directly. So the size of this hyperfine interval, which we want to do through radio frequency spectroscopy. So what we want to do is to continuously have some RF radiation, to have some population transfer from this top level to this bottom level, and then dissociate from this level via this intermediate level at V equals 4 to this dissociative state. So what we do is continuously dissociate while we have our RF radiation on, and then the increased amount of dissociation serves as our spectroscopy signal. So there's actually a few things which we could do differently before. So since we are only using these lasers for dissociation and not for spectroscopy, we don't care about being Doppler free, because all the spectroscopy is happening with the RF source. So we can dissociate directly from this V=4 level with the laser that we also use for Doppler cooling. So we have a little bit simplified setup. So there's a Zeeman effect in HD+. So we have first 6 rotational levels populated, which constitute about 62, well, exactly 62 hyperfine levels. And in the presence of a magnetic field, the Zeeman effect lifts these degeneracies, which means that if we have between 50 and 100 Hg+ ions, we expect less than 1 ion in each magnetic sublevel. So that is a little bit of a problem. So here you can see the Zeeman splitting for the top hyperfine level in the interval, and for the bottom level, and then taking into account the allowed transitions. These are the Zeeman shifts for all the allowed transitions between this top level to this bottom level in the hyperfine interval in the vibrational ground state. So we expect to have less than 1 ion in each magnetic sublevel. So what we want to do to increase the signal is to scan simultaneously over multiple magnetic sublevels belonging to the same polarization of our RF source. So taking into account these transitions with their transition probabilities and assuming some line width, then the spectrum could look something like this. And here you can see the sigma plus transitions, the pi transitions, and the sigma minus transitions. And if we had enough population in all of the levels, then we could simply scan over this entire frequency range and try to resolve this spectrum. But we don't have enough population, so we don't expect to have enough signal even from probing a single level. So what we want to do is to scan over multiple levels at the same time. So here we choose the pi transitions, which is important because they have less contribution from the Zeeman effect. So then what we want to do is to scan over them simultaneously, effectively integrating the signal from all of these transitions. So to be able to do this, it's very important to know precisely what the magnetic field is. So we know exactly where to put our RF frequencies. So then we have to characterize the DC magnetic field. So we have beryllium in our trap for the sympathetic cooling of Hg+. And the Zeeman effect in Hg+ and beryllium is comparable because of the spin of the unpaired electron. So then we can use beryllium as an in situ magnetometer. So we use this transition for our laser cooling transition, and the spontaneous decay back into this level is what gives us the fluorescence in the camera. And then with our antenna and our RF source, we can induce this spin flip transition. This is a very long-lived level. So we can put our beryllium ions in the dark state, so they don't take part in this cycling transition with the laser cooling. And then in the camera, this would look as we would see a decrease in the fluorescence. So here we follow the approach of a Japanese group, which present their work in this paper. So this is a result which they got, and this is a result which we got. So we're able to do a fit of this frequency with 0.4 kilohertz uncertainty, which means we can determine the magnetic field with an uncertainty of 0.2 milligauss. The Zeeman effect for this transition is 2.1 megahertz per Gauss. And then scanning over this we have Helmholtz coils in all directions with voltage controlled current source. So we can independently control the static magnetic fields in all directions. So then if we scan over the voltage for one of the coils, in this case the z-axis, then we can measure at every value the magnetic field. So the magnetic field is the result of all of its contributions in all the different directions. And if we fit the data, then we can see that in the limit here, where the z component of our magnetic field goes towards 0, our quantization axis becomes less well defined. So you see the uncertainty going up, and we can see that this fit tends towards the residual magnetic field, which we have in the other two directions. And from this, we can, for higher magnetic fields, get our calibration for the Helmholtz coils. So we can get a voltage or current to magnetic field conversion ratio. Then also we want to characterize the AC magnetic field. This is a measurement, actually the mean of 18 measurements, which were done by our previous postdoc, Matthias Germal. And here we can see some different components of the magnetic field noise. So we can here see some pink noise, some 1/f noise, and some white noise. And then these are actually the 50 Hertz mains hum and the odd harmonics of this contribution. And these are 833 components, and 833 and the harmonic, which originate from our turbo pump, which is very close to our trap. Then if we built a simple optical block equation model, added the noise phenomenologically to investigate if this magnetic field noise could actually cause this broadening. And it looks like it can. So we actually see a 30 kilohertz line width where we expect something much smaller. So that's good to know, because then we expect similar behavior in the line width in our spin flips in HD+. So then back to the measurements of HD+. So we have the magnetic field characterized, so we can get back to our measurements. So again, to summarize, we want to measure this spin flip frequency with RF. So this is a single photon spectrum, which was a model made by Jeroen and Sojana Matthias. And here you can see the single photon spectrum for a dissociation time of 7 seconds for a number of different temperatures. You can see that it's Doppler broadened. We expect to be at around 15 millikelvins, judging from IR spectroscopy that we did. And you can see that for this transition, it corresponds to this frequency in the spectrum. So then looking at where we are on this axis, we see that for this transition, we expect to have a fractional HD plus dissociation of around 20%. So that's the baseline. So then if we have our RF source on, if we do the spin flips, so we transfer population to J = 4, then of course we expect to have a little bit more than this 20% dissociation. So that's the idea. We scan this RF frequency, we measure the amount of dissociated HD+, and wherever this frequency is resonant, we have the most amount of dissociation. So how do we actually measure this dissociation? Because we cannot see the HD+. We can only see the fluorescence from the beryllium. So what we do is we use secular excitation of HD+ to heat the beryllium crystal. So here you can see the Doppler profiles for beryllium. Normally we're at around 50 millikelvin. Then we have this Doppler profile. And then we use our cooling laser detuned around 80 megahertz. And then when we have some HD+ in the crystal, which we then excite, we can get to around 100 millikelvin, which changes the Doppler profile like so. And then this increase we would see as an increase in fluorescence on the camera. And then if we then do some dissociation, we're left with a little less HD+. So if we then do secular excitation again, then we are maybe at 80 millikelvins. So then we have a slightly different Doppler profile, slightly less fluorescence. So that's how we, in the end, measure the amount of dissociated HD+. So here you can see the fluorescence as a result of the secular excitation before and after dissociation. And then this difference is the amount of dissociated HD+. So then these are the results that we got from scanning the RF frequency. So it's still a work in progress. So be aware these are preliminary results. So here we subtracted the field-free transition of the m equals 0 to m equals 0 transition frequency. So what we still need to do is we need to gather more data to increase the precision. Right now, this fits as an uncertainty of around a little more than 1 kilohertz. We want to be below, so we need to gather more data. Also, we need to make a line shape model. Now we simply fit a Gaussian, but might turn out that we need to fit something slightly different. And we haven't done any analysis for systematic effects. We also don't have an error budget. So that's all things we still need to look at in the future. So to summarize, we did direct measurements of the hyperfine interval at the vibrational ground state to be able to try and find this discrepancy which was previously found by our predecessors. So like I just mentioned, still need to have a line shape model. We want to do combination of optical block equations for the RF and Einstein rate equations for blackbody population recycling. And then there's the systematic effects and budget, error budget analysis. And once we finish with that, we also want to measure the hyperfine interval at the V equals 9 excited state. So then we can compare the two and see if it is in agreement with what they previously measured. With that, I would like to acknowledge the following people. And this is also where we got our grants from. Thank you for listening. Are there any questions?
Thank you very much. It's already, Ben was the first, so.
Thanks for the talk. How well can you model the RF field shape in this non-trivial geometry?
We don't know yet. we haven't started.
Thank you. Very nice talk. So from what I've seen in the plots, it seems like the line width that you get is not much narrower than for the optical measurements due to the magnetic field noise. So couldn't you get a huge improvement with some passive magnetic shielding? So is that somehow planned?
So we are planning to do something about this magnetic field noise. So right now we have a turbo pump. We have an ion getter pump, which we are planning to replace the turbo pump with. There's never a good moment to open your chamber, right? So we've been putting this off a little bit. And then we're also going to investigate where all this noise comes from. We have a lot of switching power supplies. We have a lot of AC-DC converters which produce noise. Apparently the fan in our camera produces noise because it is controlled by pulse width modulation. So these are all things that we are aware of that produce noise, which we are going to investigate on how we can reduce this. And this should also reduce the line width of our eventual signal.
Further questions, comments, critics? Doesn't work anymore?
I have a question to your RF source. So you were talking about polarization. Can you tune the polarization of your RF excitation, or how exactly? I didn't really understand. Sorry.
Okay. Yeah, so here we have a magnetic loop antenna, which there the polarization is pretty well defined. Then you can turn the magnetic loop antenna to get different polarization components. We also have a different antenna which we tested, which was a flexible polymer antenna. And there we had a mix of different polarization components. And then there it was important to have some to have a magnetic field at which the splitting was enough so that these individual polarization components would be split.
Thank you.
Okay, further questions? Oh, here is there. Grzegorz, I will pass.
Hello, so I have a question regarding your magnetic field calibration. So when you measured the transition to find out where's the zero field, and then you saw like the dispersion.
This one?
Ah, yeah. So exactly there, how could you find out where the offset value is? So, I mean, now you set it to 0 at some point, but how could you find out where the offset is?
You mean the residual from?
Exactly, because it doesn't look like the center is in 0.
Ah, yeah, so these are, we did measurements over the entire voltage range, but then as our magnetic field in the Z direction approaches 0, we don't have a quantization axis anymore, so we can't actually measure at 0, but we know that the magnetic field is the result of the square of, the square root of the square of all the components. So that's the function which we fit here. And then this fit gives us the residuals.
Repeat the question.
Sorry? So she's asking if we know what By and Bx, what they are. So no, we don't know. So this residual is the combined contribution of these two. Yes.